Hello again, this is Carson Meredith, and in this lesson we're going to be talking about types of high-throughput strategies that people approach high-throughput materials development with. And the outcomes that we're going to focus on are a number. First, we're going to distinguish between materials discovery versus knowledge discovery. We're going to talk about how people might make libraries with either discrete composition or gradient composition variations. We'll talk about a couple of ways to measure experimental properties on libraries, and then we'll highlight coupling experimental with computational methods and databases. First, there are two basic approaches that people take to the goals they want to achieve with HTMD. One goal might be materials discovery. So on the left side you see the image of a phosphor library with 25,000 different phosphors, and our goal might be to identify, for example, a red phosphor with a certain efficiency or brightness, and we could use this library to find one. But there's an equally important goal that people try to achieve with HTMD, and that is knowledge discovery. Here the goal is to not simply discover a material, but rather to discover relationships in materials, such as structure, property, processing relationships. So here you see a picture of a ternary or three-component gradient library of metal oxides. You could use this to discover the phase diagram, the phases that the three elements form together at different temperatures. So when people go to make libraries, there are a number of approaches that they might take. One of the simplest and most universal is to make discrete libraries. Here the idea is that each position on a library contains a distinct or discrete sample. This is very commonly done with liquid or solid type samples. What I'm showing here is an image of a very common 96 well plate format where it's essentially an 8x12 array of liquid wells. And there are many types of liquid robotic handling instruments that can conveniently mix in this format. However, in some cases, for example, coatings, it's more convenient to make a gradient library. Here you may have a substrate, and on that substrate you coat a gradient where you go from one composition to the other in one direction. You can also have properties like thickness and temperature varying in the other direction, where you get a two-dimensional gradient library. Here the main point is that the samples are not in discrete positions, but they are continuously varied across the library. Once you've made a library, of course, you want to measure some properties on that library, and there are two major approaches. The first is to do rapid serial or rapid point-to-point measurements. So there are many types of instruments, both custom and commercially available, for measuring spectral, optical, mechanical, electronic properties, and many others at point-to-point positions on a library. And what you see here is a video of a high-throughput mechanical device we designed in my lab that's measuring mechanical properties from point to point on a polymer library. But in addition to doing point-to-point measurements, some measurements take long enough that it's not convenient to do them one point at a time. Instead, it makes more sense to do them in parallel. So this may work for measurements like infrared spectroscopy, where you can have a focal plane array detector that looks at an entire region of a library all at once. NMR, where you can insert, say, a composition gradient into an NMR magnet and look at a range of compositions simultaneously. An example from my own work here below is a parallel gas absorption screening instrument, where we can look at up to 36 individual specimens and look at gas absorption or sorption into those specimens simultaneously. The caveat here is that you have to have 36 sensors online at the same time, so that the instruments are oftentimes designed custom by the user to do that. Generally, experimental high-throughput material science is not carried out by itself, but it's done in concert with computational methods. This is an example from a case study that I'm going to talk about later, in this class. But essentially, we were designing on a team metal organic framework materials. These are adsorbent materials. We were trying to use them to capture carbon dioxide. We started with a possible library of 30,000 compounds in structured databases, and we narrowed this down to an experimentally accessible number of compounds, several dozen, for example, that we could look at with high-throughput screening. But we narrowed this down using computational approaches. We'll talk about more about this later. When you are collecting large amounts of data through high-throughput materials development, many scientists will rely initially on a spreadsheet-type program or simply text files. However, when your database of information begins to approach 100,000 elements or 100,000 distinct experimental conditions, it becomes more efficient to switch over to a relational database, a database where you can predefine relations between the data fields. While this takes more time and effort to set up, it actually facilitates searching, discovery of anomalies, discovery of materials, and structure property relationships later. So what's next? What's next is we're going to bring in some guest speakers to talk about big data and informatics. Ultimately, once you collect a large amount of data, you're not simply interested in that data. You're interested in extracting information and knowledge from that data, and that's the role of informatics. Thank you.